Okay, hi everybody. So compute the Jacobian matrix for this map. Remember that a formula that's in blue could change on the quiz or the test. Could change, but not by a lot. It might change, like the dimensions might change, but the formulas will always be relatively simple. For example, like polynomials, or cosine and sine, or e to the something. So very, just the basic functions. Okay, so this is a map. This map, I guess, has inputs R2 and then outputs in R3. How do I know that? Well, because there's a comma there and a comma there, which means there are three formulas. Okay, we could rewrite this. Let's give it a name. Call it F, and we could write things in column vector form. x1, x2, 3x1 plus 2. And then we have the output formulas. This is the first, second, and third component functions of F. Okay. So compute the Jacobian matrix. Part A. Compute Jacobian one column at a time. In particular, and I'll sort of add another part of my words for this answer will be that each input variable will have its own column of the Jacobian matrix. And so how do we, so here the inputs are, there's two of them. So that means the Jacobian will have two columns in this particular example. There will be a column for x1 and a column for x2. Okay, so the partial derivative with respect to the first input variable will be, well, I take the partial here, that'll be 3x1 squared. And then I take the partial with respect to x1. Partial with respect to x1 will give just the constant, x2. Remember, this is like, well, anyway, let me just write the answer here. Gives what column? So it'll be a column, it'll have three entries, 3x1 squared, x2, and 3. Okay, and then the second input variable, now we let the second variable vary, and that will give another column of the Jacobian matrix. In this case, the second variable doesn't even appear here. There is no x2, so the derivative is 0. Here there's an x2 and it has a constant x1. And here there's no x2, so the derivative is 0. Okay. So each input variable has its own column of the Jacobian matrix. And then, I guess, so the Jacobian matrix is, and then the second column. That's it. We're done with part A. Okay. So we just take partial derivatives, and partial derivatives are easy. They're just like single variable calculus. You just have to keep in mind which variable is actually varying. The rest are all held as constants. Okay? And that brings us to sort of what this means in a picture. What does that mean in a picture? Well, we're going to have curves in the input and output spaces. In this case, the input space was R2 and outputs in R3. So let's draw that. Letting each variable, well, here, let me draw a picture first. So here's the input space. Let's draw it like this. And then the output space. Okay, and then F, maps inputs to outputs in some way, potentially giving some surface in R3. Like this whole rectangle might become this curvy surface, okay? And what we're going to see is that horizontal lines will become curves, vertical lines will also become curves, and they will be curves on that surface, okay? So that's what we're going to see, and let me just do it a little bit better. So if I pick some point, like let's say this is the point P equals x comma y, and then f of P will be somewhere. I don't know, maybe it's here. Maybe that's f of P. Okay, and then let's choose a color like pink for the horizontal line. So this horizontal line is when x varies. So x varies. And then this vertical line is when we let the other variable vary. This is now with y varies or changes. And so what happens is that each of these, every point here can get mapped over. F can map it to some point. F can map it to some other point. And so what happens is the entire horizontal line becomes some curve in the output space. This entire vertical line, as y varies, becomes some other curve in the output space. I don't know what it does. And so that's sort of like in our head, if we took this whole rectangle, not just these straight lines, but took the whole rectangle and we map it over, it'll become some entire curvy surface inside of R3. Okay, and then, yeah, so this should sort of make sense. Now, that's my picture. What is the question? Explain how columns are related to curves in the input and output spaces. Well, each column was just a derivative when one of the variables varied, so it should be like that straight line. And then this will be a velocity vector, and this will be a different velocity vector. So I'll just put that in words. So here's my words, letting each variable change, fixing others, gives a straight line in the input space. Okay? And then F maps that line to a curve in the output space. And here's the point now. If we take just a unit movement, like this would be I hat, or it would be the vector 1, 0 in this case, it's the movement only in the x dimension, then that will become a velocity vector. Okay, so the column of Jacobian matrix is the velocity vector, and that's what I'm explaining. Velocity vector of that curve. That's what it is. Okay, and so if we had two input variables, then there's two columns of the Jacobian. So then there's let me choose a better, darker green color. So that would be the vector sort of j hat maybe, or 0, 1, or e2 or whatever. It's only moving in the second dimension only. Then that little unit vector will become some sort of velocity vector. Okay. So that's what we have. So did I answer it? Let's see. Explain how the columns are related to curves in the input and output spaces. Well, the straight line is the curve in the input space. F maps that straight line to a curve in the output space. And okay, well, what about the columns of the Jacobian? They are the velocity vectors to those curves. Each input variable has a straight line that becomes a curve and has a velocity vector. Each input variable gives a column of the Jacobian. And that's it. Yeah. Later, we will integrate over surfaces by taking this little square and finding this parallelogram and its area using the square root of the determinant of the gram matrix of the columns of the Jacobian. Those will be our vectors that we put into the gram matrix. This one and this one. Later, when we're integrating. But you can sort of never mind about that for now. I'm just telling you where we will eventually be using this. Okay. Let's look at my other answer. I was quizzing myself. You can see the picture looks a little different. I labeled it first column of the Jacobian, second column of the Jacobian. And I said that the columns of the Jacobian are velocity vectors. And I explained that if we allow only one input variable to vary, that gives a straight line in the input space. And then F throws that straight line over into the output space, and it becomes potentially a curvy, nonlinear curve. Yeah. Okay, so remember that you should be able to do this for a different formula. Maybe even with different input dimensions, different output dimensions, different variables. And so try that yourself. But before you go there, maybe just see, can you completely, without looking, solve this by yourself? By the way, for this particular map, let's actually see what that surface looks like. Here you can see I did it in GeoGebra, and that surface is actually kind of weird looking, in my opinion. In particular, it has a very interesting point there. One point that's interesting, that's f of p for some particular p. And in linear algebra, math 250, linear algebra, you will learn to calculate something called the rank of the Jacobian matrix. And when the rank drops, you will find weird points like this. And actually, in this case, it corresponds to the fact that at a particular point, namely when x1 is equal to 0, the second column is just the entire 0, just 0, 0, 0, and that would be a weird point. But anyway, it's sort of interesting to see what the actual picture looks like if we have a computer draw it for us. And you can see the two curves. I chose the point p equals 0.9 comma 1. And then f of p is right there. That's f of p. This is the output space. Output space. And I didn't even draw the input space. The input space is somewhere else. And here's the point p right there. And here's f of p over here. And then through the point p, if we take this line, it becomes this line. And if we take, I think this line, this vertical line, it becomes this curve. So that's interesting. And you can play with this. You can change the value of the x and y coordinate and see the curves on the surface change. They'll maybe go through different curves.